All right. So, similar figures. So we have seen how that when one shape is mapped using a dilation, it produces another shape that has side lengths that are scaled by the same scale factor and the angle measurements that are the same as the pre-image. So all the angle measures of the shape are congruent, but the sides are not. That's the difference between congruency and similarity. Now, that means they have the same shape, but different sizes. And they're known as similar figures. All right. So similarity is very close to congruency. Like I said, the only difference is that the size changes. All right. The shape's still the same, so the angle measures are still the same, but the side lengths change. Now, when two geometric figures are called similar, which we represent by just a squiggle. So, you know how with congruency we do the equal with the squiggle on top? Similarity is just the squiggle. All right. All pairs of corresponding sides are proportional, which means they have been scaled by the same factor to all corresponding and all corresponding pairs of angles have equal measures. All right. So the sides are proportional. When you hear the word proportion, what do you think? Say it again. Right, so a piece of something if we're talking about proportion. So piece of something, what's another name for that? Fraction. All right, so proportional means fraction or ratio. It's a ratio of each other. So in other words, with the warm-up today, the proportion for the sides would have been 3/2. All right. So if I put them together side by side, let's say I took the first point. If I took the bigger side, put that on top, so that was my new figure, over the smaller, we get 3/2. Let's say I took the y value to be r. So we started with -10, and we got -15. If I simplify that down, we still get 3/2. So that's what it means to be proportional. You put the new over the old, you should get the scale factor. All right. Now, let's look at exercise 1. So they claim that triangle ABC is similar to triangle DEF. So again, this little squiggle right here means similar. Now, the part A says use tracing paper to verify that all the corresponding angle pairs are congruent. They are. All right. So angle A would be congruent to angle D, angle B, angle E, angle C, angle F. All right. Now, let's determine the lengths of the missing side. So let's call side AC X and side EF Y. All right, so those are our two missing sides. How do you think I would find side X? Take the 20 and divide it by X, that's the first part. But I need something to compare it to so I can solve for X. What can I do then?
So if the angles are congruent, it's going to be the same shape.
Right. Yeah, good job. So we look at the one side that they did give us that's an accurate proportion, which was the 7 and the 14. All right. Those are the corresponding sides, so it should equal 14 over 7. Now, there's two ways you can go about this. You can either cross multiply to make a linear equation, or you can simplify the 14 over 7 and then solve it like that. All right? So I'm going to cross multiply here. So I'm going to do 7 times 20, and then x equals 14. So if I do that, I would get 140 is equal to 14x. Divide by 14. X should be equal to 10. So side AC would be equal to 10. All right. What about y? Yes. Yeah, you could figure out the scale factor and divide by it. So this scale factor is really straightforward of what it is, but sometimes the scale factor isn't as obvious. So that's where this would come in handy. But let's say, what would be the scale factor for this? So if I ask for the scale factor, what do you think it would be? 2. So if you divide 14 by 7, you should get 2. So to find y, how would I find it? You just do 8 times 2, so that would be 16. So your y should equal 16. So I showed you both of these ways because, again, sometimes the scale factors are weird fractions. So sometimes solving it this way is a little bit easier. All right. Now, give a dilation of ABC that would produce an image A prime, B prime, and C prime that is congruent to DEF. So we kind of already said this. All we would say is that we would dilate triangle ABC by a scale factor of 2. And that would give us A prime, B prime, and C prime, which again, that would be congruent to DEF because they have the same scale factor. It's the same proportion. So A prime, B prime, C prime would be congruent to DEF because they have the same scale factor and congruent angles. So again, that's why I started with going back and talking about dilations, because that's literally how you would find similar figures. It's basically just a geometric version of a dilation, or it's just a non-graph version of a dilation. All right. Now, we formally define two similar figures in a manner that is similar to how we define two figures that are congruent. So if we're talking about a similarity transformation, two geometric figures are similar if there exists a similarity transformation that will map one figure onto the other. So this transformation is either a dilation alone or a sequence containing a dilation in combination with more rigid motions. Now, just to review, what does it mean by a rigid motion? This is back from Unit 1. Clark. Right, it's a transformation that doesn't change the size or shapes. In other words, it produces what? Congruent figures. Good. So, what are the 3 rigid motion transformations? Translation's one. What's another one? Reflections and rotations. All right. So sometimes the similar figures, they may not look exactly the same. They may be turned a little bit or reflected, but just like we did congruent figures, you just find the corresponding sides, corresponding angles. All right. So in this diagram, we're going to describe the similarity transformation from ABC to DEF. So first off, they already marked our congruent angles. So let's list our corresponding sides first. All right. So what would my first set of corresponding sides is? So let's say A to C. What would be its corresponding side? DF. Good. So we look at the angle with one tick, the angle with three ticks. That's where we're going. What about from C to B? What's its corresponding side? Say it again. It would be SE. You go from the three tick angle to the two tick angle. So that means that AB would go to DE. All right. So now that we know where our corresponding sides are, we can now figure out what's kind of going on. All right. So first off, what is one transformation that you think happened? Definitely a rotation of some kind. All right. If I had to assume, I would say it looks like it's about 180 degrees, mainly because it looks like this started here and then ended here. So it's either, or maybe 90. Let's just say it was a rotation, okay? We're not going to be stupidly specific. So we know a rotation happened. What else happened? All right. So what's that called? So flipped. So what's that called? A reflection. And then one last thing happened. Is it the same size? Definitely a dilation. All right. So the rotation and the reflection would produce the congruent figures. But then as soon as we do that dilation, that's when it becomes similar, not congruent anymore. All right. So we're going to skip exercise 3 because it's pretty much more of the same. But let's look at exercise 4. So it claims that triangle ABC is congruent to triangle DEF. And it wants to know what scale factor we need to dilate ABC so that its image is congruent to DEF. All right. So first off, let's just list the points for ABC. So A is at what point? So it'll be -7, 1. What's B? It'll be -3, 1. And then what's C? -3, -7. All right. Now, it maps onto DEF. So D, E, and F. So what are the points for D, E, and F? So what's the point for D? 9, 8. E? So E would be 3, 8, and F would be 3, -4. Now, if we look at these points and what the graph looks like, there are definitely more than just dilation going on here. All right. So looking straight at the points won't really help us in terms of figuring out the dilation. So let's think of another strategy that would help us figure out the dilation. Now the reason I have you guys write the points down is because we'll use that in a second. All right. So let's talk about how I can figure out the dilation of these two figures without using the points. What do you think a strategy would be? So think about how we already found similar figures with just triangles that they gave us. What do they typically give us? So look back at exercise 1, for example. What did they typically give us in order for us to find the scale factor? They gave us what feature? 2 sides. All right. So I need to find 2 side lengths. All right. How do you think I can find one of the side lengths? So guys, don't we have some vertical horizontal lines? So then we just count the units. Yeah. So for AB, if we count the units between A and B, because that's our horizontal line. 1, 2, 3, 4. So the side length is 4 units long. If I look at BC, it'll be 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 units long. Now, if I wanted to find AC, what can I do? Pythagorean theorem. So if I wanted to find AC, I could use the Pythagorean theorem. All right, because it's definitely a right triangle, because if you have a horizontal line meeting a vertical line, it's automatically perpendicular. All right. So to find AC, we could use the Pythagorean theorem. So a squared plus b squared equals c squared. But for right now, we're not going to worry about that. Really, all I need is 2 side lengths. All right. So I want to find the corresponding side lengths. So AB corresponds to DE. So if I count, that's 1, 2, 3, 4, 5, 6. And then EF would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Now, the reason I wanted at least 2 side lengths is because you want to have something to compare to. All right. So we know that we're probably going to set a proportion for one of the corresponding sets of side lengths. But whatever we get for that, we need to double check with another set of side lengths in order to make sure that that's our actual scale factor. Because human error happens. All right. So my recommendation, if it ever asks you to find the scale factors from a triangle and they gave you the triangles, use at least 2 sides. All right. to double check what it is. So how would I find the scale factor now? So how'd you find the scale factor? We would set up a proportion, right, guys? So you set up a proportion. So remember, that's your new side length over the old. So let's say I used A, B, and DE. All right. DE is proportional to AB. So that means that I would have 6 over 4. Which if I simplify 6 over 4, what does that simplify down to? 3/2. Now, I'm going to double check that the proportion from EF to BC is also 3/2. All right. So EF is proportional to BC. So that would give us 12 over 8, which was that simplified down to? 3/2. So our scale factor is 3/2. All right. Now, let's assume that we went ahead and did our dilation. All right. So, if we did our dilation, it would give us the new set of points. But then we have to do some more transformations. Now, for time's sake, we're not going to do that because I can trust that y'all know how to do the composition of transformations because you already learned that. But essentially, if you eyeballed it, it looks like it would have been a translation or reflection over the y-axis and then a dilation. All right? Does everyone understand that part? All right. So, a common scenario that you see is that similar triangles is when a line segment is drawn parallel to one of the sides of the triangle. So, this is kind of like mid-segment theorem. So remember, mid-segment theorem is when a segment is drawn from the two midpoints of two sides of a triangle. All right? And it's parallel to the base, or the third side that's not used. Now, this figure right here is not using the midpoint theorem. All right, and we can tell because it definitely looks like DE is not halfway between AC and DE. All right. But we do now have two similar triangles. So in the diagram shown, BD lie on AC and AE such that BD is parallel to CE. And we're going to give the dilation for ABD to ACE. All right. Now, what this looks like is ABD is this triangle right here. All right, it's the little baby triangle that gets formed right there. Whereas ACE is the big triangle that we flat out see. Now, we're not going to figure out numbers or anything, but we are going to at least list the proportions. So, if we were listing proportions, what is one set of proportional sides? Say one more time. Right, B, D, and CE. So we can say, because we want to do new over old, so we're mapping ABD onto ACE. That means ACE is our new, ABD is our old. So we would do CE over BD. What's another set of proportional sides? So corresponding sides with another set of them. Say what? AC and AB. So I would write AC is proportional to AB. And what's my last one? AD and AE. Good. So AE is proportional to AD. Now, what has to be true about all three of these? So if we put numbers in for each of these, what has to be true about all three of these proportions? They have to be the same scale factor. So in other words, these three proportions have to be if they have the same scale factor, that means that they are not similar. The proportions are. So guys, the scale factor we get from the proportions. So if it has the same scale factor, then the proportions are congruent or equal. All right, they're equal. So the proportions have to be equal to each other. All right. Now, the other part of similarity is that you would need the angles to be congruent. So angle ABD would have to be congruent to angle ACE. Angle BAD would have to be congruent to angle CAE. And angle AEC has to be congruent, or you know what, angle ADB has to be congruent to ACE. So these are the conditions for similarity. The sides have to be proportional to each other, meaning if you set up the proportions, they should be equal, and the angles got to be congruent. All right, those are the conditions of similarity. Does everyone understand that? So if we look at our last question here, what's incorrect, or circle the proportion that's incorrect based on what we know about triangle ABD is being similar to ACE. So let's just go down the line. AC over AB to CE over DB. Is that correct? Yes, we wrote it up here. Now, angle A has to be equal to angle A over angle ABC has to be equal to angle ACE. Is that correct? So if we look back at the picture, angle A would just be that top part of the angles, the one angle that they both share. And then angle ABD has to be the angle ACE. So yeah, that's true. What about AD over AE has to be equal to AC over AB? Is that true? No. Why? What's wrong with it? Look at how it's lined up. This fraction right here, what's going on in comparison to this one? Lucas. Right, so they mismatched the wrong sides. AD does not correspond to AC. All right. Or in other words, it's not on the same triangle. So it would have to be, if we fixed it, this would have to be flipped. All right? So whenever you set up your proportions, you got to make sure if you put a triangle side in the numerator, the side that's equal to it has to equal the same triangle. Same thing with the denominator. You got to keep the triangles that they come from consistent. All right? That's what's wrong with it. And then number 4 will also be correct. All right, any questions on that? All right, so 5 or pages 3 through 4 is the first part of your homework for the weekend. But we're not done with notes quite yet. So now turn to page 5. This is a little bit shorter because we already talked about it yesterday. Pages 3 and 4, that's part of the homework. We're not quite done with notes because now we're on page 5. So, similarity criteria, we already talked about this a little bit already. So, 2 similar figures will have congruent corresponding angles and corresponding sides that are proportional. So one of the set lengths is a constant multiple of the other. Whereas congruent triangles, there are always, like congruent triangles, there are ways that we can tell true triangles are similar and limited amount of information, known as the criteria. So guys, where this comes into play is that there, just like there are postulates for congruent triangles, there are postulates for similar triangles. All right. So if they didn't give us the side lengths or the congruent angles, like they didn't tell us the measures or anything, we can still figure it out based off of the postulates. So for example, with congruent triangles, that would have been side, 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 angle, side, angle, side, angle, 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 side, and hypotenuse side. Those are the 5 postulates. For similarity, there's not as many. All right, so not as many to memorize. I think there's only 3. All right. So again, if they're similar figures, we already talked about this. Similar, if a dilation of one figure will make it congruent to the other figure. All right. So the angles are still congruent, but the sides are now proportional. So if we give a dilation that would make AB congruent to DE, note that it does not need to map onto DE just to be congruent. All right. So they told us up here that angle A is congruent to angle D and angle B is congruent to angle E, which they already marked for us. Now, let's just, for pretend, make up a dilation. So we're going to make up a side length and come up with a scale factor for it. All right. So let's just say that A is 4 and, or so AC is 4 and DE is 6. All right. What would you guys like the scale factor to be? So we're just making it up. No. Small, guys, small. Let's just say 2. So let's say we had a scale factor equal to 2. So if we wanted to map to DE from from AB to DE, if we have a factor of 2, we start at AB, we're going to DE. What would side AB be? It would be 3. So remember, it would be 6 over x with a scale factor of 2, so we want it equal to 2 over 1. So we could cross multiply that. 6 is equal to 2x, so x would be equal to 3. So for DF would be 8. Now, let me ask you guys this. If triangle ABC was dilated using the dilation from part A, would angle A prime be equal to angle A and angle B prime be equal to angle B? Yes. So if we're talking about this would be A prime, C prime, and B prime. So even though we did a dilation, the only thing that changed was our side lengths. So yes, they would still be congruent. And it's because the shape didn't change. And why would it be congruent to DEF? So if we did A prime, B prime, and C prime, well, let's say we would have two angles congruent, and they just asked us to find DE. Well, if that's also the same thing as A prime, B prime, then it would be congruent by what postulate? So if we use these two angles and the side angle, side. Nope, not side angle, side. Angle, side angle. Duh. I'm pretty sure that's what you said, Natalie. I just mixed it up. Now, this leads into our different criteria. So these are our different postulates. So the first postulate is the angle postulate. You may also see it as angle. All right. So the angle criterion for similarity, you may see it as AA. You may also see it sometimes as angle. All right. All it is if the two angles of one triangle are congruent to two angles of another triangle, then the triangles are similar. So remember how I said when we were doing congruence postulates that if all three angles were congruent, we couldn't conclude that they were congruent? That's because we don't know if the sides are the same or not. We don't know if the sides are proportional to each other or congruent to each other. So if you just have all three angles, we just get the same shape, not the same sides. So now it's called angle because of the third angle theorem, meaning that if two angles are congruent, that third angle has to also be congruent to its corresponding angle. So that was a very weird way to say that. So two sets of congruent angles. So if we have two sets of congruent angles in two triangles, the third set of angles would also have to be congruent through the triangle sum theorem. All right. Now let's look at the diagram here. So in the diagram shown, QR lie on MN and MP such that QR is parallel to NP. So in other words, these two segments are parallel to each other. So remember, the little arrows mean parallel. Based off of the angle criterion for similarity, what allows us to conclude that triangle MQR is similar to triangle MNP? Now, we don't know what those angle measures are yet. We're not going to make anything up. But what could we use, so we learned back in 2A, that can help us figure out if the angles are congruent? Give me a hint. 2.3. What was 2.3 all about? Say that again. Not midpoint. Not vertical angles. Say it again. Corresponding angles. So in other words, angles formed by parallel lines cut by a transversal. All right. So let's say we extended these two parallel lines. So we just extend them. All right. Our transversals would actually be side MN inside MP. So if we actually drew the transversals, they would look like this. Do you guys see it now? All right. So you can use the parallel line transversal theorems to conclude that angles are congruent. So, for example, how is Q congruent to N? So angle Q congruent to angle N. How would those be congruent? By what theorem? So angle Q and angle N. What type of angles are they? Corresponding. So angle Q is congruent to angle N because they're corresponding angles. And we know that corresponding angles are congruent. What about R and P? So how do we know that these two angles are congruent? They're also corresponding. So angle R has to be congruent to angle P because, again, they're also corresponding. Now, since we got two sets of congruent angles, we can assume that angle M is congruent to itself. But what's another reason we could state that angle M is congruent to angle M? When we were doing proofs, what property was that? It's the reflexive property because they're reflexive. All right. But in reality, we only need two of the angles to be congruent in order for AAA to be justified. So with these two sets being congruent, they are similar by AA, or angle. That would be the postulate that gives us that. Now, if we have the diagram here and MQ is 8, NQ is 6, and NP is 21, they want to know the length of QR. So they want to know this length right here. How could I figure this out? So we know that the sides have to be what to each other? Proportional. All right. So which side would be proportional to QR? So what's QR's corresponding side? Come on, guys. You know what corresponding sides are. It would be NP. Good. So, even though, don't get confused, because it's a small triangle here with a big triangle here. All right? These two are still corresponding sides. All right? So, that means we could set up, if we did the proportion from new to old, we could set it up as 21 over, let's say, QR. Now, I need something to compare it to. What can I do with the other two side lengths that I have to compare to it? So what would be the length of MQ? So MQ. 8. So will that go in the numerator or the denominator? Say it again. Not quite. So we're going the numerator or the denominator? Nope. It goes in the denominator. So guys, remember, you got to keep the triangles consistent. So QR is in the denominator, MQ is in the denominator. Because they're from the same triangle. Is that what you said, Sutton? No. Oh, no, Sutton. I'm so sorry. This thing's loud. But if I don't keep it on, the figure gets awful. All right. So, now what would be the side length of MN, which is the corresponding side to MQ? 14. How'd you get 14? Right. We got these two side lengths, so we just need to add them together. That will give us 14. Now, to make our lives easier, we can simplify that proportion 14 over 8 down. So we can rewrite this as 21 over QR is equal to what? So if we simplify 14 over 8, what will we get? 7 over 4. Good. So, since this is kind of a weird fraction, we're just going to do some cross multiplying. All right. So I'm going to do 21 times 4 and QR times 7. So 7 times QR should be equal to 84. Say that one more time. QR is the side length. So it's literally side QR. So yeah, if that's throwing off, so you can put the little line over it. I'm talking about side QR. You could put an X there if you wanted to. I'm just putting the actual side length so you guys know that's what we're finding. All right. Now, how would I solve for QR? Divide by 7. So side length QR has to be equal to what? 84 divided by 7. That's a multiplication table. 12. So if they're proportional to each other, QR has to be 12. Now, you could have also just multiplied 21 by 7 over 4, but you would essentially would have just done the exact same thing as that equation. You would have multiplied 21 times 7 divided by 4. All right, we're almost done. We just got like 2 more criteria. So the last 2 criteria that we can use to prove that 2 triangles are similar is side, side, side. So this one also has a side, side, side one, where all 3 pairs of corresponding sides are proportional and similar. So it's the same proportion between all 3 sides. That's what that means. Side angle side, or SAS, just means that 2 of the sides are proportional to 2 of the other sides, and the included angle is similar. Or no, the included angle is congruent, which then makes it similar. So why these make sense? Well, side, side, side makes sense because if all 3 sides of both triangles, if those proportions end up equal to each other, if we took them between their corresponding sides, if they're equal to each other, well, we know that similar figures are just essentially a dilation of the original. So they have the same scale factor, they have to be similar. All right. Whereas side angle side, same thing with the 2 sides, makes sense that they're similar. But then the angle in the middle means that not only are those two sides proportional, but they form the same angle. All right. Which that means that the rest of the triangle would follow suit. Okay. So let's look at these 2 different diagrams. So our side, side, side example. All right. That means that we would have to put up all the corresponding sides together. So let's say we're going from ABC to DEF. What would be the corresponding side to AB? What's the corresponding side to AB? DE. So that'll be our first proportion. Remember, it's always new over old. And if you don't know which one's which, like if it doesn't flat out say that ABC mapped onto DEF, it doesn't matter where you put it as long as you keep where you put the sides or what triangle you use in the numerator and what triangle you use in the denominator consistent. All right. So what about BC? What will be the corresponding side to BC? EF. And then AC. What's the corresponding side? DF. Good. So if we took those proportions, if we substituted in the side lengths into those proportions, they should be the same thing. So DE is 10, AB is 5, so that should be equal to EF, which is 8, over BC, which is 4, which should be equal to DF, which is 6, over AC, which is 3. So if I simplify all three of those fractions, should I get the same number? Yes. What would that number be? 2. So 10 divided by 5 is 2. 8 divided by 4 is 2. 6 divided by 3 is 2. So since all three of these are the same proportion, we can say that triangle ABC is similar to triangle DEF by side, side, side. But all of the proportions have to be the same. Now, let's say I flipped the side lengths, like they didn't tell me which one mapped onto what. We would still get the same thing, but instead of 2, it would be 1/2. All right? So a similarity, it doesn't really matter. It won't necessarily ask you the scale factor, technically, unless they flat out say that this triangle was your original, this triangle is your new. All right? Any questions on side, side, side? All right, side, angle, side. First off, we got to check that we have two sets of proportional sides. So one of our side lengths is DE. What's the corresponding side of DE? AB. So that has to be equal to EF over what? BC. So if I substitute in my side lengths for these two proportions, they should be exactly the same. If they're not, then automatically side angle side doesn't work. So that means that we would have 15 over 10 is equal to 21 over 14. Now, if I simplify those fractions, will I get the same thing? What's 15 over 10 simplified? 3/2. What's 21 over 14 simplified? 3/2. They're equal. So, since those two proportions are equal, the two side aspects is fulfilled. All right? But we still need the angle assets being fulfilled. But for the angles, they have to flat out be congruent. So the angle in between those two sides would be angle ABC has to be congruent to angle DEF. And is it? Yes. Because 110 is equal to 110. So because of that, everything has been fulfilled. That means that triangle ABC is similar to triangle DEF. So for the SSS, this has to be the criteria. The proportions of the sides have to be equal to each other. For all three sides, for SAS, two of the sides have to be proportional, and then the angle in between those two sides has to be congruent. So remember, this angle has to be between the two sides. All right. So last thing, and then we're done. So for exercise 5, which of the following sets of information would not be sufficient to prove that triangle ABC is similar to triangle RST? So let's just go through each one. So triangle S is congruent to triangle B. So they're saying these two angles are congruent. And then triangle C is congruent to triangle T. And these two are congruent. Does that make similar triangles? Yes or no? So think about what our 3 criteria are. Yes. By angle, angle. So those are similar by angle, angle. Now, it's saying that AB is proportional to RS. So for proportional, I can't remember the symbol off the top of my head for proportional. So we're just going to use a check mark. All right. So they're saying AB is congruent to RS and AC is proportional to RT. Then they also said that angle A is congruent to angle R. So would that make a true statement? Yes, that would make them similar by what postulate? Side angle side. Now, this next one, it's saying RS, so here to AB, ST, so here to BC, and TR to CA. So they're saying all 3 of those sets of sides are proportional. So does that make a similar triangle? By what postulate? SSS. So we're assuming our answer is the last one, but let's check it just to be safe. So RT to AC, so RT to AC, those are proportional. TS to CB, so saying these two are proportional, these two are proportional. And then TS, so these two are proportional, these two are proportional. But then they said that they want angle B congruent to angle S. So look at what I highlighted in blue. Does that work for any of our postulates? No. If we were talking about this, it would be angle, angle, side. That is not one of our similarity postulates, so we don't have enough information to say it's similar. All right. So this one, there's not enough info. All right. So that means that 7 and 8 are the other 2 pages of your homework. So your homework tonight or for the weekend is 3 and 4, 7 and 8. All right. Any questions on how to figure out if triangles are similar or not? All right. So you got about 10 minutes left of class. So you can probably do a little bit of the homework to get started.